In honor of this 25th annual NCUWM, I'm delighted to introduce our first speaker, one of the conference co-founders, Dr. Judy Walker. Dr. Walker earned her undergraduate degree in mathematics from the University of Michigan and her master's and PhD in mathematics from the University of Illinois at Urbana-Champaign, specializing in algebraic coding theory. Following that, she joined the faculty in the Department of Mathematics here at UNL, where she is now the Aaron Douglas Professor of Mathematics and Associate Vice Chancellor for Faculty and Academic Affairs. Dr. Walker has served on many important committees and boards, for example, the AWM Executive Committee and the AMS Board of Trustees, and has supervised many students at both the graduate and undergraduate levels. She's an award-winning educator and scholar who's been honored for her accomplishments in both areas. Her work has been recognized with the HAMO Award from the MAA, the Louis Hay Award from the Association for Women in Mathematics, and the Outstanding Alumni Achievement Award from the Department of Mathematics at Urbana-Champaign. Moreover, Dr. Walker is one of the inaugural Fellows of the American Mathematical Society, a Fellow of the Association for Women in Mathematics, and a Fellow of the American Association for Advancement of Science. I hope I got all that right. It is with great pleasure to introduce Dr. Judy Walker.
I can't even tell you how excited I am to be here. This is, like, I put it in red, 25th, there's 2 exclamation marks, right? So I have notes that I'm gonna get out, and I have a clicker. So I need like 4 hands because I have notes, I have a clicker, I have a mic, I have a water. Yeah, no. Always helpful. You gotta love assistant professors. All right, so what I'm gonna do is I'm gonna give you I'm gonna talk about me, because, you know, that's what I'm gonna do. But I'm gonna talk about influential moments in my mathematical career and the mentors who influenced them. That's basically what I want to talk about today. And we'll talk about some math along the way too, don't worry. So that's me. I know. I was looking for a senior picture. I think that might actually be sophomore year in high school. But I grew up in Southern Illinois, small town in Southern Illinois. Anybody from Southern Illinois? Probably not. No. It's beautiful, by the way. Beautiful area. And I went to college, as Christine said, at Michigan. And the reason I went to Michigan is that my entire senior year of high school, people were saying to me, next year when you're in Urbana-Champaign, and I said, yeah, no. And so I went to Michigan. So when I was in high school, I didn't have AP. My high school didn't have AP. AP existed. I'm not quite that old. But I didn't have AP. But I had this amazing teacher who I don't have a picture of, and whose name I don't even actually remember. But she taught a group of us from freshman year through senior year of high school. And we ended up getting through Calc 2 with proofs in high school. Then I went to Michigan, and either because he was trying to be very nice and supportive and make sure I would succeed, or because there was a little bit of sexism there, didn't believe me that I had had 2 semesters of calculus and insisted I take Calc 1. And I finally talked my way into an honors class with Luke Helmick. So this is my first mentor that you're going to see. So Luke is currently the Dean of Arts and Sciences, I think, at the University of Hawaii. But he was a postdoc at Michigan, and he was my professor for 2 semesters, for first semester calculus, second semester calculus. And he pretty quickly decided I wasn't supposed to be in his class and sent me up to the high honors class. And I lasted like a day because I didn't like the people. And so that's my first lesson that I didn't even put in my takeaways at the end of the talk. But it's not fun if you don't like the people, right? Like the people. So that was Luke. So he got me through the first 2 semesters. And then this is Jeremy Teitelbaum. Somehow my mentors have all become deans. So Jeremy was also a postdoc at Michigan. He then was dean at University of Connecticut, and then was actually provost, or maybe just interim provost at University of Connecticut. And now he has the best job in the world, which is full professor at the University of Connecticut. But Jeremy was my professor for third semester calculus, for Calc 3. And that was the first course that I really found hard. And the reason that Jeremy is so influential at this point, he's actually going to come back. We're going to see him again. But Jeremy said it was okay that it was hard, and that I just needed to keep working and I could do math, which never occurred to me that it could be hard, but I could actually do it. So that was Jeremy. That is Mort Brown. So Mort Brown I never had a relationship with outside of him being this professor in this one class that I took. But this class was the first analysis course, and it was hard. It was very hard. And we were doing a proof of Bolzano-Weierstrass. Anybody remember that theorem? You know that theorem? All right, we're doing a proof of Bolzano-Weierstrass, and he's stuck. He was stuck in the proof, right? And it turned out that he was stuck because he had a less than sign where he needed a less than or equal to, or vice versa, and I don't remember now. And I very timidly, and he couldn't get past it. I very timidly raised my hand and I said, shouldn't that be? And I said the right thing, and he got very excited and told me I was right and finished the proof, and then asked me to see him after class. And what he said to me, what Professor Brown said to me was, you know, you could be a pretty good mathematician if you just had some self-confidence. So that was pretty huge. So, you know, no good deed that goes unpunished, and a week later, I went to his office and said, hey, you know how you said that I could be I want to do this REU. And so he wrote a letter of recommendation for me to the Rose-Hulman REU. Does anybody here do the Rose-Hulman REU? So I was in the very first year of the Rose-Hulman REU. So REU, who knows what REU stands for? So Research Experience for Undergraduates. It's an NSF-funded program. There's a lot of them around the country. There were not a lot of them at this time, but there are now a lot of them around the country. This is Gary Sherman. He ran the REU. And this REU was in computational group theory, which meant that we used a computer program to run experiments. We could put in groups to this computer program and ask it questions about the groups. And then we would look at all of this information, and we would look for patterns, and we would make conjectures, and we would prove them, and now we have a theorem, right? It was the best experience. It was so awesome. So, whoops, wrong way. So that led to my first publication, right? So rewritability in finite groups, and I'm going to tell you about that in just a second. This is me over here, J.L. Levitt. That's me. You'll notice that. So we'll see more about him later. So let me tell you a little bit of math. Sorry, I need water. Okay, so how many of you have had group theory? All right, good. So this definition is not new, what an abelian group is, but maybe this way of writing it is new, right? So the way I'm writing that a group is abelian is that the probability PR2 of G is 1. And what is this probability defined to be? It's defined to be the number of ordered pairs that it doesn't matter what order you write them in, divided by the order of the group squared, right? So the total number of ordered pairs. So that's a probability. It's the probability that two elements commute, right? So a group is abelian if that probability is 1. All right? That works. So this is a really fun fact. How many of you knew this, the 5/8 band? Yeah, it's super cool, isn't it? So if a group is not abelian, then at most 5/8 of the ordered pairs commute, right? So what that means, I did an example here to tell you. Whoops, one more, there it is. So for example, if you have a group of order 8, right, then there's 64 ordered pairs, right? 5/8 of 64 is 40. So if you can find 41 ordered pairs that commute, then that group is abelian. Every ordered pair will commute. So this is actually, nobody knows really who proved this originally. It's not that hard to prove. You count conjugacy classes, it's pretty cool. But this is a theorem. So when I say folklore, that means that it's just kind of out there. We don't really know who proved it. So what we studied in this REU was 3 rewritable groups, right? So it's a generalization of commutativity. So we look at the probability that if we take an ordered triple of elements, then you can rewrite it in some way. So if a group is abelian, it's definitely 3 rewritable because you just switch the x and the y or the y and the z. But you can also cyclically permute them, right? And that still counts now. And what we proved was that the probability is always at most 1/2 if it's not 3 rewritable, right? So in other words, if you've got that group of order 8, right, then 8 cubed is 512, so there's 512 ordered triples. And if you can find 257 of them that you can rewrite, then you can rewrite any of them. Right? Isn't that fun? And the way we did this was by throwing a whole bunch of groups into this computer program and looking at those numbers and saying, we can't get anything in this gap. I wonder if that's always true. Right? So you make the conjecture, you write down a proof eventually, and boom. All right, so I was hooked. So this was the summer between junior year and senior year of college, right? Okay. So, oh, good. So what time is it? I'm doing great. So then I went to grad school, and Champaign-Urbana got me back, right? So I went to Champaign-Urbana for grad school. That's a picture of Altgeld Hall, which is this gorgeous, gorgeous math building on campus. And what I want to say about this before I go on is I had a TA position. So I was a teaching assistant. What that meant was I didn't pay to go to grad school, and they paid me, right? That is normal. That is common. If you want to go to grad school, you should get paid for it, right? If you want a PhD. There are also master's programs out there that are professional masters, and those you usually have to pay for, and that's fine, right? That's a good thing too. But if you're looking at a PhD, you should get paid for it. So I had a TA position. I had a couple different fellowships during the time that I was there. So, but within, I think, the first 2 months that I was at Illinois, Jeremy Teitelbaum was back. Right, so Jeremy had been a postdoc at Michigan, remember, when I was there as an undergrad. He then finished his postdoc, went to University of Illinois at Chicago for a tenure-track position. And all of a sudden one day I see this poster up in the math department with a picture of Jeremy, who was much younger than this, by the way, at the time. Picture of Jeremy, that he's going to be our colloquium speaker. So I'm like, I'm going to go see my friend Jeremy. So I go to the reception for this colloquium, and Jeremy is like, Judy, how are you, right? And then he says, have you met Nigel? Right, so Jeremy introduced me to Nigel Boston, who turned out to be my PhD advisor. Right, so that's how I met my PhD advisor. But what was super cool was that Nigel was also brand new to University of Illinois. He was a first-year tenure-track assistant professor, and he didn't know any students, but he had this grant with this summer support for a grad student. So suddenly I had summer support. And I was doing research, in fact, in group theory, right? So it's kind of similar, actually, to the work that I had done in my REU. And we were doing it over the summer, and it turned out that that research was actually, so Nigel is not real, I mean, he's kind of a group theorist, but he's more of an algebraic number theorist. And the group theory questions that he had me working on that summer were related to algebraic number theory, to class field theory, in fact. And that turned into my thesis topic, except for Christine said that I did algebraic coding theory, and that's because I hated my first thesis topic, right? So class field theory was not for me, did not like it. went to Nigel, said, I need something else, and he said, you know, I think there's a connection between algebraic geometry, which I loved, and coding theory, which I knew nothing about. Go learn about it. Okay. So let me tell you a little bit about coding theory. So the idea of coding theory is you've got some information that you're going to send across a channel, and you know there's going to be some errors. And the idea is you want to add redundancy in a clever way so that you can detect and correct those errors. That's the big picture, right? So let's look at this picture here. So what you do is you take your information, you pass it through an encoder. So that's going to add on that redundancy. So what comes out of there, we call the code word, right? So the information was maybe K zeros and ones, and what comes out is N zeros and ones. You pass that code word through a channel. What comes out of the channel is a received word. So that's that code word with some errors introduced. Maybe some zeros became ones, or some ones became zeros, or maybe some of the numbers just went away entirely. Then you take that received word, you pass it through a decoder. What the decoder does is it says, all right, if this is what came out of the channel, most likely this is the code word that was sent. And then, so that gives you an estimate of the code word. I made up this word, unencoder. That strips off the redundancy, and you get your estimate of your information. So the n-fold repetition code, for example, or the r-fold repetition code, says you just repeat the information r times, and then the decoder uses majority vote, right? So if you're using a repetition code of length 5, and what comes out is 3 ones and 2 zeros in some order, you say, well, probably it was 5 ones that was sent, and your information was probably a 1, right? Okay. So by making R large, you can correct as many errors as you want here, but it's really inefficient. On the other hand, if you just add an overall parity check, so you start with a string of n-1 zeros and ones, and then you add on an nth symbol so that the total number of ones is even, right? Then you can always tell if an error happened or not, right? If 2 errors happened, you might not be able to tell. But if 1 error happened, you'd be able to tell. But you can't correct it. You don't know where that error happened. All right. So let me give you some formalities. So code of length n over FQ. Who knows what FQ is? Yeah, very few. So FQ is the field with Q elements. Just think of it as F2, zeros and ones if you want, right? So a code of length n is a subset of just vectors of length n, right? So look at all the vectors, take a subset of it. C is linear if it's a subspace, and then the dimension is the dimension as a subspace. The minimum distance is the minimum number of places in which 2 code words differ. So the minimum number of coordinates in which 2 code words differ. And if you have a linear code of length n, dimension k, and minimum distance d over fq, then we use this notation, nkd sub q code. Fine. All right. So that's coding theory. So the goal is find codes that correct many errors. So that means you need large minimum distance, that are efficient, which means you have large dimension, and which have efficient decoding algorithms, because you don't want to have to do a lookup table. You want to have a way of knowing what was the most likely code word that was sent, right? So Shannon's theorem from 1948 says good codes exist, right? This is Claude Shannon. This is not, unfortunately, some woman named Shannon. But it is a fantastic theorem. But the proof of this theorem is probabilistic. It's existential. It says they exist. It doesn't say how to find them, right? And my favorite quote here is, any code of which we cannot think is good. I love that quote for so many reasons, right? One of which is just the incredibly stilted language. Right? But any code of which so in other words, there are good codes out there, and there's a lot of them. There's a lot of good codes out there, but somehow still it's hard to find them. So that's coding theory, is find these good codes, right? That's what Christine does, that's what I do. So algebraic geometry codes use algebraic geometry to find those good codes. And I'm not going to tell you really how we do that, but I'm going to show you these 3 books that I read that summer. I didn't read them all. This one's little, and I did read it. So that one's by Van Lint and Van der Geer. That one's by Stichtenoth. That one's by Sosman and Vladeut. And they get progressively harder, these 3 books. But these are the fundamental books in algebraic geometry codes. And so I read them. And I said, okay, Nigel, I know what algebraic geometry codes are. What now? And he said, I don't know. I left this out. So the reason that algebraic geometry codes are so good or so cool is that they're really good. So remember that D is the minimum distance, and that tells you how many errors the code can correct. R is the dimension, that tells you how efficient the code is. Let's divide both those numbers by n, the length of the code, just to kind of normalize things, right? So we've got a trade-off between the relative minimum distance and the information rate. And you kind of want to find codes that are out here as much as possible. So this curve here is the Gilbert-Varshimov bound. It's been known since mid-50s, I think. This line up here is the Plotkin upper bound. It's been known probably about the same amount of time. So the Gilbert-Varshimov lower bound says there are codes that are at least this good. Plotkin upper bound says that no code is better than this. But nobody could find codes that were actually better than this, or technically a sequence of codes that were better than this, until algebraic geometry codes. And that's what this TVZ line is it says there are codes that are at least this good. TVZ is Sosman, Vladeut, that's that orange book from the previous slide, and then a third person zinc. All right, so algebraic geometry codes, super, super cool because they're solving this problem that, this is interesting. It printed things multiple times. Okay, it solves this problem that nobody could solve before. All right, so then I needed some more mentors. Right, so went over to electrical engineering because nobody in the math department at the time at Illinois, there's now a couple people, but at the time nobody in the math department did coding theory. So I went over there and I met Alex Vardy, who was awesome, and Dick Blehout, who was also very cool. And they started talking to me about algebraic geometry codes, and they were super excited. And they were super excited because their students in electrical engineering couldn't do algebraic geometry. But they were interested in algebraic geometry codes, and so I had this in, right? And so I got to talk to them a lot. So came up with a problem in algebraic geometry codes, worked on it, got some results, wrote a dissertation, you know, no big deal. So in the spring of my second to last year of grad school, I already had most of my results. I was writing things up. I was going to stay one more year in grad school. And I went to an AMS sectional meeting. How many of you have ever been to an AMS sectional meeting? Some of you. So AMS is American Math Society, right? They have meetings twice a year around the country, like 4 in the fall, 4 in the spring. Sylvia, who's here in the front row, was an associate secretary for, no, were you? No, Georgia was. You were not. Confusion, sorry. Yeah, right? I would love to be confused with Georgia Bankhart. Yeah, sorry. Okay. We'll get back to Sylvia later, though. We will see Sylvia soon. Went to an AMS sectional meeting in Chicago. And Vera Pless, who was at the University of Illinois at Chicago, which remember is where Jeremy Teitelbaum was, Vera was organizing a special session in coding theory. And I was like, I'd love to give my talk in this special session, but the special session was invitation only and nobody knew who I was. And so I signed up to give my talk in a general session. And I went to all the talks in the special session. And Vera comes over to me and says, "Who are you?" I mean, she said it a little bit nicer, but she didn't know who I was, and here I was showing up in her special session. And so I told her who I was, and I told her why I was there, and I told her I was giving this talk in the general session, and she said, "Oh no, that will not do." And she told everybody in the special session that they needed to give up 20 minutes of their lunch because she was going to move my talk from the general session to the special session, and everybody was going to see it. Right? This is huge. This is huge. So Vera did that. And one of the people, it looks like a mugshot, poor Patrick. One of the people that was at this talk was Patrick Soleil, who was from France. And Patrick came up to me after my talk and he said, "You know, there's this conference every summer or every other summer at Lumini in algebra geometry codes." I said, "What's Lumini?" And he says, "It's a conference center in Marseille, France." And I say, "Huh?" And he says, "You should come." And I say, "Well, how do I do that?" And he says, "Well, I'll get you invited." And he did. So I went to Lumini, and guess who I met? I met Vandergeer and Stichtenoth and Svassman. Right? This is the summer before I graduated with my PhD. So suddenly these people were real people. Right? These names that I had heard were real people. So that was super cool. And I wanted to say something on the previous slide, actually. What do you notice about Vera, by the way? She's the first woman, right? I'm a year from finishing my PhD, and it's basically the first woman that paid attention to me. Not to blame the women, because there just weren't any at Michigan when I was there. And there were a couple at Illinois, but they were not anywhere close to my field. All right, whoops, wrong way. Okay, so I got to meet these cool people, but I also got to go to Lumini. So this is the conference center, and you'll see there's these picnic tables out here. So the conference was very small. It's like, I don't know, 80 people maybe 50, I don't know. Small, invitation only. And after dinner, we would go out and sit at these picnic tables and drink wine and talk math. It was amazing. It was the coolest thing in the world. And on Wednesday afternoon, Wednesday afternoon, we went on an excursion to I think they're called the Calanques. Is that right, Roger? Yep, to the Calanques, and which is part of the Mediterranean Sea, right? Walking distance from Lumini. And I actually went to the conference a week early with my best friend from preschool, and we went to Paris for a week, right? My plane ticket was paid for by my department because I was going to this conference, right? My extra expenses in Paris, that was on me. My stay at Lumini, I think, was paid for by the department, but I think very discounted by the conference center, right? Super cool, right? Don't y'all want to be mathematicians now, right? All right. How am I doing on time? Okay. So then I got my degree. So this is me with my PhD robe. This is M.E. Walker. This is Mark Walker with his PhD robe. And our friend Suzette actually took that picture because she wanted us, she wanted to see the hoods. So after we got our degrees, we came here. Right, so why? Why did we come here? Well, came here because of those three people, basically. Right, so this over here is Jim Lewis. He was chair of the department at the time. This is Roger Weekend. He was graduate chair at the time, right? 96? Probably. Yeah, he was also chair of the search committee that hired me. This is Sylvia Weekend. Sylvia was also a professor in the department, and she was president-elect of the Association for Women in Mathematics. I don't think I even knew there was an Association for Women in Mathematics. And she's this president-elect, right? And they're all in this department. And I met with these two at a conference. They kind of interviewed me at this conference, and it was the most amazing conversation. And so then they invited me out for an interview, and I loved it. And the reason I loved it was the happy, successful female graduate students, and there were a lot of them, right? So Christine told you, or Petronella told you, about the history of the conference, right? And the work that they did to build that culture here is just amazing. So there are actually several people here who are current or former happy female graduate students, happy, successful female graduate students. Raise hands. These are my people. These are why I came here. So, all right. So how did they do this? So what happened was that in 1989, where is Jim? Why is Jim not here? What? Oh, okay. All right. We'll give him some slack. So in 1989, Jim Lewis became chair of the department, and he looked and he realized that there were no women that were going to get PhDs from this department in the 1980s. Right? And there was one on track to get her PhD in the 1990s. And he said, oh, this will not do. Right? And he worked with the rest of the faculty, with Roger, with Sylvia, with everybody else, to build a culture in which women graduate students would succeed. And you know what he did? He built a culture, they built a culture in which every graduate student could succeed. Right? It wasn't just the women. So in the 1990s, not only did they give PhDs or award PhDs to something like 15, I want to say, women during the 90s, they also awarded more PhDs to men in the 1990s than they had to men in the 1980s. Right? So it was just a better department. And the mantra was, if you create an environment in which people are expected to succeed, they will. Remove the barriers, celebrate the successes. All right, so Mark and I decided to come here, right? We came here, we became faculty, and then in, I want to say, fall of 1997, so I came here in 96. Fall of 97, I saw an announcement for the presidential awards. And so I nominated the department for this award based on all this work that had been done before I got here. I get no credit, right? Not only do I get no credit, but I wrote the nomination. I thought that I filled out the form so that Jim Lewis, who was the chair, would be the contact person, right? Apparently, I can do math, but I can't fill out forms. So by the time we realized this, they had already done it, so we got the award. They had already done the background check on me, and it was too late to fix it. And so I got to go and receive the award. So there's a whole story there. Literally. So, it's possible that this is the only year in which the president actually met with the presidential award winners. He hadn't before. I don't know if he has since. He did, because how many of you know what the STAR report is? Go Google it. Those of you who don't. So the STAR report was released to Congress on a Wednesday, I think, and then to the public on a Friday, or maybe it was Tuesday and Thursday. There was a day in between, right? That day happened to be the day of the award ceremony, and he needed a good photo op. And so he came and met all of us awardees. There were several, I mean, it wasn't just me, right? There were several of us that got this award. And then about the institutional awards and individual awards. And so then, as I think it was Petronella was saying earlier, we were challenged at this conference to use the $10,000 grant. Was it you? It was you? Okay, good. To use the $10,000 grant to do something that furthered the work that had led to the award. And so we created this conference. So there's the conference. Yay. So that's the story. There's also a story about the picture, but I'll tell you that another time. Okay, good, 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 good. So who are my mentors now? This is very different. This is a very different picture than the pictures that I was showing you along the way. Right, so what I've learned now is that, first of all, peer mentors are huge, huge. So look around, bake some mentoring, right? All a mentor is somebody that gives you advice, right? So these are my mentors. Some of them are senior to me, some of them are my peers. Some of them are mathematicians. Bryna is the president-elect of the AMS. Jill is a former president of the AMS. Leona is the director of diversity and inclusion for the AMS. Peter and Rebecca have the same position that I do, this vice provost essentially for faculty affairs. Peter's at Purdue, Rebecca's at Minnesota. Dondi's the former EVC here. Kathy's the current EVC here. And Renee, here in the corner, is somebody that I work with every day on faculty affairs things in the office. Those are my mentors. What is interesting is these are the people I mentor, right? So Bryna, Leona, Rebecca, Peter, Renee. John Lark was my postdoc around 2002, long time ago. This group right here, a few of them are here today. Actually, maybe just one of them is here today. Just one? That's so sad. But Lauren's here. Everybody say hi to Lauren. So these are all former grad students at Nebraska, current PhDs. Jessalyn, it was her wedding that this picture was taken. And she was my student. The rest of them weren't my student, but I still claim them. Two of them were Christine's students. Three of them, no, two. Two were Christine's students. This picture is in my office. I have it on a shelf in my office. And what makes me so proud of this picture is that I couldn't make it to Jess's wedding, but they took this picture and they sent it to me. It just made me so happy. And at the joint math meetings recently, I started getting texts with pictures from Lauren and from Jess with them all together. And it was just so nice, so nice. So who else do I mentor? Well, I kind of, at least by extension, mentor the people that come to NCUWM. I don't know who else I mentor, right? That's the weird thing about mentoring. I don't know if all of these people know that they're my mentors, right? I think mentoring and role modeling is pretty similar, right? So those are my mentors. So what are the takeaways? What are the takeaways? So first of all, please take advantage of this weekend. 25 years, right? I just can't. It's just amazing. So I am just in awe of you all. Second is find your mentors where and when you can. If you find women, you find women. If you find men, right? And in particular, make the men work, right? But also use your peers, right? Use your peers. Being a mathematician is tons of fun, right? The mathematics is fun, but also you get funding for grad school, you get to travel, all kinds of great stuff. And lastly, be a mentor, right? Give your advice. Behave in a way that people will want to emulate, right? It's worth it, it's fun, it's rewarding. That's all I got. Thank you.
higher percentage of students who started actually made it to the end of the program, or were more students actually being admitted to the program? The program grew. Okay.
The program grew. I think it's probably also true that more were making it through, but the program did definitely grow. And I didn't mention earlier, but I should mention that the percentage of women in the graduate program here has actually been maintained at about 40%, which is way more than a lot of places. I was looking at a department recently, and a math department, which I will not name, but I was looking at a math department recently, and they had like 2 women in their graduate program, and no students of color, by the way. Crazy. Crazy. No, I think it's people raising their hands that they have empty seats. I got excited for a minute there, too.
That's a question.
You talked about some of the different research opportunities that you got, and obviously a lot of us are probably doing research here. What were some of the biggest challenges that you faced while doing research, and how did you work through them?
Hard. No, it's really hard. So the biggest challenge for me with doing research is that I liked it so much that it felt selfish, right? And that to me has been the biggest challenge, right? So I would prioritize teaching over doing my research because somebody else needed, like my students needed me to be prepared for class. Research I was doing for myself, right? When my kids were born, at that point I basically couldn't do research that wasn't joint because I needed my collaborators to hold me responsible for it. That's the hardest part for me. But early on, the hard part was really just getting stuck and having to convince myself that it was okay to be stuck and to keep trying or to put it away and take a fresh look at it the next day or a week later or whatever. You just can't get discouraged. And I will tell you that Calc 3 class from Jeremy Teitelbaum is what taught me that, really, right? Because that was the first time it was hard. We had how many, so of our faculty types that are here, how many of you did Immerse? So we had a program here that Tom Marley ran for a while called Immerse, and it was a bridge program between undergraduate and graduate. And when we were designing that program, one of my goals was that everybody, so it was like a 6-week program, is that right, Tom? Yeah, 6 weeks. And my goal was that within the first 2 to 3 weeks, every student hit a wall and got discouraged. Right? That's what I want.
She didn't tell us that.
Well, no. Everybody needed to hit a wall and get discouraged so that we could spend the rest of the program building them back up, so that when they went to grad school, which was going to be hard, they already knew what that was like, right? That is, I think, the hardest thing, right? Because you don't do math, you don't go into math because you find it hard, right? Yeah. But at some point, you're going to find it hard. Yeah.
What are some opportunities for international travel or travel in general for grad students?
So the question is, what are some opportunities for international travel or travel in general for graduate students? So there's conferences everywhere all the time. Well, there weren't for a while, but now there are conferences everywhere all the time. There are conferences everywhere all the time again. So look for those conferences. Get an advisor, ideally, that has some funding to help you go to those conferences, right? But also, the AMS has travel grants for graduate students to go to the joint meetings or to go to sectional meetings. There's also not REUs, but summer programs for graduate students. So there's the Park City Math Institute, which will fund you. There is MSRI has graduate programs, and NSA has internships for graduate students. And there was one more that I wanted to mention. What was the other one that I wanted to mention? Okay, there's a lot more. There are a lot of opportunities out there. The hard part is not finding the thing to go to, it's finding the funding to go to the thing that you want to go to, right? But those opportunities that I was talking about at the end, those fund the students that come. Yeah. Otherwise, you need to line up funding from your department or your university or your advisor or something. Yep. Over there.
I'm pretty loud. I don't know if I need a mic.
Everybody needs a mic.
Thank you. Oh, warned you. You talked about how you had a professor who told you to be less timid, but that's kind of a scary proposition. How did you work to be less timid, and how do you think you ended up achieving that? Because it seems like you did.
That's hilarious. I am actually super introverted, in fact, right? Like, I do really well on a stage because I figure people want to be listening to what I have to say, but in social situations, I actually get very awkward. Still, he did not tell me I needed to be less timid, though. He told me I needed to have more confidence, right? Which is related, but not the same. He was telling me I needed more confidence in my abilities, right? How do you get that? By having people tell you that you need more confidence in your abilities, right? Surround yourself with those mentors who tell you that you're cool. Yeah, totally. Totally. Yep. Yep. Here in the purple, towards the front. And then there's one like 5 rows behind her.
Thank you. I'm wondering, did it ever discourage you? I mean, I know the percentage of women increased, but like, did it ever discourage you to see like a bunch of men, or even just having to compete with men? How did you deal with that? I mean, it seems like you're very confident, and like the biggest struggle was just being motivated to do your PhD dissertation. But how did you deal with the men? Sorry, I don't mean to offend the men.
No, how did you deal with the men? I mean, honestly, it was by having male allies the whole time through, right? So my freshman year, I didn't have that, but I had Luke, who was a fantastic professor, right? My sophomore year of college, there were these 2 guys who, of course, got to start in Calc 3 as freshmen, but the 3 of us actually ended up taking basically our entire math major together for the rest of our time at Michigan, or the rest of my time at Michigan, and then they got an extra year because, you know, they got to start in Calc 3. Not that I'm bitter or anything. But having them, and then of course I met Mark at that REU the summer before senior year, and then we went to grad school together. And having those men around that I knew had my back and I knew respected me, let me distinguish between this is a crappy thing that happened to me because I'm a woman, and this is a crappy thing that happened to me because I'm a person, because I'm a grad student, because it was a crappy thing, whatever, right? And being able to distinguish was actually super helpful. Right? But I can tell you stories about the crappy things that happened to me because I'm a woman, right? And I'm not going to do that because that's just depressing. But they are kind of funny. So, you know, corner me later and I'll tell you. But I'm not going to tell. I'm not going to tell a whole room full. But really, it's about the allies. It's really about the allies. Yep.
My question just was, what does having a mentor mean to you, or how do you know that someone truly is a mentor, or is just someone that gives you advice, and what does being a mentor mean to you?
That's a great question. I use the word mentor very loosely, right? Like I said, I don't know that everybody on the page that said, these are my mentors, knows that I think of them as my mentors. And I also don't even know if everybody on the page that says, these are who I mentor, know that I mentor them, right? Like, I don't know. I use mentor and role model that you know pretty interchangeably, right? And role model, again, can be a peer, right? But, I mean, Bryna, for example, so Bryna was a plenary speaker here. That's when I first met her, actually, was when we had her here as a plenary speaker. I did not like her at all, by the way, when she was here. And over the years, we've just gotten to be very, very good friends. We probably talk 2 or 3 times a week. And we are constantly asking each other for advice on things, right? So right now, she is probably my biggest mentor, right? But I don't know that either one of us, we actually had a conversation about that the other day, and I don't know that either one of us had thought about it in those terms until we had that conversation, and then we were both like, oh, yeah. So, yeah. But a lot of places will have formal mentoring programs, and I'm actually not a believer in formal mentoring programs. I think that organic mentoring is much more effective and enjoyable, frankly.